Hello and welcome. Today I am going to implement Radix sorts, and it's the first time I've ever written Radix sorts, so I guess we will just see how it goes. I don't know too much about it, or at least I have never looked up like someone else making it, but I do know the basic principles. So we can say that here we have a block of memory, and we are chopping it up into different structs, integers, whatever, and they each have values like 0, 5, 2, 30, 1, 78, I don't know, 3, 56. And we just want to sort them. So obviously there's a couple of different ways of doing this. So we can just go and grab all of the we can go through all the values and like just look up the lowest ones. That's a valid strategy. But the way that Radix sort works is that you're having a value. Let's say it's 0x 10, 20, 30, 40, or something like that. So what you can do is you can sort by just the first byte, and then the second byte, and the third byte, and the fourth byte. And then at the end of that, you have already sorted the entire array because everything is in order. What you can also do is that you can look up the biggest value. So let's say we go one pass at first just to see what we are looking at. We can see that maybe the largest value is hex 3000. Well, that means that we can just do it. We can just do the pass twice, and we don't really have to do the extra 2 more times because there's no value above hex 3000. Another thing that we could do is we can count the number of each instance. So let's say we are having 3000 and we're looking at the first bytes. We are going to have a number of duplicates because there's just like not enough slots for each value. So like there has to be, you don't know which ones it's going to be, but you know that, you know, for 3000, there's going to have to be like one that is, you know, a couple dozen times, one that is maybe 100 times, something like that. So if we are creating a hole or like some memory, some RAM, where we are putting all of these into, but we need 256 slots, then it's kind of a problem if you need to have potential memory for each value to go up to, you know, 3000 times. So instead of having 256 boxes that are each the size of the largest value, or the number, the count of the array. So instead of having that, what we can do, we can just count them. So we say we have 3 zeros, we have 50 fives, we have maybe 76 230s, and then we can just allocate memory that is exactly the same. And then whenever we find, you know, a 0, we put it, the first 0 here, the second 0 there, the third 0 there. And then when we get to the 5, maybe there's no, there are no like 1, 2s, or 3s or 4s. We know that whenever we write 5s, we can, the first number we see could be a 5. And we just know that we are writing 5 from the third point because that's how many values that come before it. So doing that, we can have the same amount of memory that we need to sort. We cannot quite sort in place with this method, but we can just have the same number of memory instead of having 3000 times 256 if we would be sorting by a byte. Or we could sort by, we could have 64 buckets, or we could have 8 buckets. That's also possible. But then we have to iterate through this. If it would be 8, then you would have to sort this one, and then this one, and then this one, and it would take twice as many iterations through the entire array. Like depending, it could maybe sometimes make sense to use that. But as a general method, I think this is good, what I'm going to make with 1 byte, 256 buckets. But again, as I said, we only need the same memory that is already occupying that the array is already occupying, and doubling that. And for any reasonable thing that we're going to sort, maybe we're going to sort 1 megabyte of data, or 5 megabyte, or 10 megabyte. But I don't think we're going to sort 1 gigabyte of data. And even then, we would just be adding another gigabyte, and it wouldn't be the end of the world. Of course, if it would be 50 gigabytes, then then we have a problem. But I don't think there's any realistic scenario where we're going to have to do that. So that's sort of it for my how I was like thinking about it. So I think we can just get to coding. Obviously, there's more things here. I want this sort to be... there's one more thing that I was thinking about. So most of the time, you're going to be sorting by U8s, U16, U32, and U64. And what is interesting here is that if you have a U8, then we are having the original array, and then we're having our duplicate array, and we are sorting everything into here. And because it's only one step of sorting, then we can copy everything back at the end. So this has the sorted array. This is good. And then we are copying it back. And that's, a little bit wasteful. We could be using this one instead. We could just like swap this pointer for this pointer, but I don't want to do that. So I feel like, yes, it's an extra step, but in terms of usability, I am willing to accept that. Now, for the other ones, so U16, again, the same scenario. Well, the cool thing is that you are sorting it once here for the first byte, but then you can sort it back on the other pass. And on the other pass, you get the data back into the original array. So that works pretty nice. This one, as you can see, this is 2, and this is 4. So then again, you have the first byte, second byte, third byte, and fourth byte. And for this one is 8. So you have the same thing where anytime you're having a round number that you are sorting by, you get this a memory copy for free, kind of. So that's pretty nice, because I feel like most of the time we're not going to be sorting by U8s anyway. We're going to be sorting by U16 or U32s. Now there is one more scenario, or 2 more scenarios, I should say, because we do have technically U24 and U48. And now they are not like types in the sense that we are sorting by them, but they are 3 and... we have more actually. So U24 U48. I am bad at head math. So we have U40, U48, U56, and U64. Like, this is kind of how we can think about it. Because again, if this is 1, 2, 3, 4, 5, 8, 6, and 7. So most of the time we're going to be sorting by this or this, but at the same time, if we're finding that the highest value is fitting within a U24, then we're, instead of sorting it one extra time for no reason, I think it makes sense to just like do the sort and then literally just copy it back. It doesn't make sense to sort 4 times instead of 3 to avoid doing the copy, because the copy takes place anyway. It's just that we are copying it back. So that's just something to think about. The other thing is that, like I was writing here, I'm having my array is a void star, and then I'm having all of the offsets to the struct. So I have my U32 data, or hello, really? Whoa, what is going on? I've never seen this before. Paint, hello. So this is kind of the scenario that I'm thinking about. So we are having some kind of struct that we want to sort. And the size of this is, in this scenario, we're having 8 plus 1 plus 4, which together makes 13. Now, I think this is actually going to be rounded up to 16 in almost every scenario. But we can't make this assumption. We just have to get told what is the size of the struct. So that's the size over here. Then we have this. This is the sort value, right? And it is this is 9 bytes after the start. And this, I think I also cannot assume, because the compiler could very well just throw in a buffer here, like U8 unused 3. I think the compiler is allowed to do that. Just throw that in there. Of course, it's not going to be visible to you as the programmer, because it's thrown in there at compile time. And you can tell the compiler to not do this, but it's not something that you can rely on. The nice thing is that you can get that with offset off. this macro right here. So what offset off does is it's taking a type, a struct, like here our alphabet, and then I'm asking for the offset of glyphs. So then it's going to go, okay, well, this is a pointer, so it's 8 plus unsigned int, so it's a 4, probably. Again, this, I guess, technically could be 16, depends on the platform. But no matter, regardless of what platform it's made for, it can figure it out at compile time, the offset from the beginning to here. And then we get the actual value. So not 9, but probably 12, something like that. Then we also need to know, are we sorting up or down? So is the highest value going to be at the very top or at the very bottom? We need to know if this sort val, is it going to be a positive or negative? Is it going to be signed or unsigned? Because, well, obviously, if you're having FF, then that could be the highest value, or it could be -1, which is like sort of in the middle. So that's also something that we need to know, the sign. Count is self-explanatory. And yeah, that's kind of the parameters. And I think based on that, we can just write this algorithm, like I said, that we are having some block of structs. They are spaced at regular intervals. So the size of the struct. And we are chopping it up like this. And then we're just looking at, okay, we're sorting this area, sorting this area, sorting this area, and then finally sorting this area. And then everything is done. So let's try to do all of that in one function call. And as you can see here, these are just sort of overloads. So if I already know that I'm sorting by a U8, then I know that the size is 1, and I know that the sign is also 1, and otherwise it's 0, and then 2, 4, 8. And even if it's an 8, I'm still gonna log the largest, because the integer that I'm reading, again, if we're having this struct, it makes a huge difference depending on the memory layout. Let's say that I'm having this scenario. Well, if this is a U32 and I'm reading 4 bytes, then that's okay. But if this would be a, let's see, if this would be a U8 and I'm reading, because this is a void star, so I need to know the size of the integer that I'm sorting by. So if I would sort this by a U16, then I would read a combination of these two, and then I'm going to get the wrong value. Or I might even sort it by a U32, and then I'm going to go outside of the struct into the next thing down here. And this area, this memory might even be out of bounds if it's the last entry. So that's something we really don't want to do. Now you can take this U8 and you can cast it to a U32, but you can't read it as a U32. That's the only thing. So with all that said, I think we can just try to do this. So I think the best way to start is to just go in a for loop. Oh, and we don't have any because this is going to be a library. I don't have any definitions, but we can go here. Well, not there. Let's go to JSON. And let's copy this. So if they are not defined, then we are just defining them. Always use sign integers in for loops if you can. It's a personal tip of mine. Mm-hmm. Well, we already have if it's signed or not. So I could write a Radix sort. I'm not sure if there's an easy way without duplicating code to write this. Also, this makes a huge difference if it's signed or unsigned. Well, the value is going to be influenced heavily on the top. So let's say you have 0xff. Or even better, can I change this to decimal? Now, I don't know how to construct this. Minus hex that. Well, I guess it's just a matter of interpretation. So the thing is, if this is a positive number and you have 65,000, then like, I just don't know how to sort this if the value is negative. So I'm reading Stack Overflow, big mistake by the way. And they're saying, well, you can flip the sign bit. And then flip it back. Okay, that's a good one. I can sort the positive and negative separately. That's a very good idea. So let's say we are starting with so if it would be a sign sort, we need to split it. But I already know how many negatives there are and how many positives there are. I'm having a bunch of ideas now for this. So let's see. I need a buffer array. So it has to be equal or greater than in size to the buffer. And I don't really want to write any code here for allocating a buffer. I can just leave that to the user. Please allocate a buffer that is the same size before you put that in. Okay, so let's start with this one because I'm having so many ideas right now. So the first thing we need to do is SI. I guess we also need long longs. This goes here, and we are limiting it to SI. If you want larger than SI, then you have to redefine it yourself. Then it can be 64 bits. But for this, I think this is good. Size, sign. Well, the largest value can be a number of sizes. I know it cannot be longer than SLL. Mm. I have a feeling I can't really do this in so general. I can, maybe I need to write it in these individual ones, and then I can call the correct function from this one. Yeah, I think maybe let's do this one first. The other ones are like kind of automatic. You might even implement them with a macro. Oh, so we have the value. The value must be a TFL. Maybe it doesn't make sense to have these ones specifically. I kind of have to do the same ones as my defines. Is there a type undef? Yeah. We might. How would you sort by floats? It's a question for another time. Why is this not working? Carbit. Expected expression. How is that not accurate? Oh, I see. Now it's working. No? C++ 26. So I am reading since C11, you have static assert. And in C23, you have basically the same thing. I think Clangd is confused. Maybe I have to type def it. It's the same. It's the same thing. Why is this not working? Thank you for the follow, Maxim VS. This is I don't understand why it's having an issue with this. Also, these are all kind of unnecessary. We can ignore them for now. Let's see what the actual compiler says. Yeah, that's true. Or I64. Because this is the I32. So we can actually do I32 there. Too few arguments. Sure. I need to have another arena or some memory, right? What arena was I using here? I have Scratch Arena, Static Arena. I need a Scratch Arena. So what is the size here? Size count? I kind of forget. Yeah. Well, here is our struct. Here's our array. We have a glyph count and we have the glyphs. So the size is AB glyph count times size of glyph. We get back a void star. Yep. Oh, and it's not alphabet glyphs. It's actually glyphs or glyph and occurrences. Because this is the value we want to sort by. Yep. Alphabet create. Then we have to go back here. Good. Now, please. No, there's still, I don't know. Clang is having a day. Now we can finally get to sorting. So yeah, like I said, we are going over all of the values. This is my value is equal to the void array no, just like that. So this looks like black magic a little bit, but what I'm writing here is that I have my void array. I'm casting it to a U8. I'm going to the stride times I, so 0 for the first one, and then stride for the second one, then stride times 2 for the third one, and so on. And then I'm looking at plus the offset. And remember, offset was here in alphabet. Offset is this macro. And then we're casting the entire thing to an I32. So if I'm that should give me the occurrence value in alphabet here. In alphabet glyph this thing. Should give me that value. And we can test that soon just to make sure that I wrote this the correct thing. But first, let's say if the largest value is larger than, or well, if it's smaller than value, then we store that. I need to start my debugger. So now you can see here AB glyphs. The first occurrence is 3, the second one is 123, and then 172. And I think we can kind of lock that actually, just to keep it on the watch window. Oops. So the first value we get is 84. Aha. What was so wrong about this? U int 8p. Stride is 12. Is that correct? Yeah. I is 0, obviously. Offset is 8. Four, 8. And it's an I32. Guess we have to look at the memory. We are looking for 3. Which in hex is just 3. It's this one. And we're looking at array. So the first one's 76. Is this one. The next value is 47. 2F, which is this one. And then we have 3. So where do we go? With this. I see what's happening. Or do I? Do I have to do it in here? I guess. I thought I could just put it there, but I guess I need to put it in here. Doesn't make a huge difference. It's just surprising as all. So again, we have the same numbers, 46, 47, and 3. This value is now 3. It's our largest value. It's not negative. Then 123, again. It's correct. 172, and so on. And we can get our statistics. We have no negative values, of course, because occurrences cannot be negative. The largest value, 253. Maybe I should sort something that is negative. We can just literally do AB glyphs 5 or 4. dot occurrences equals or multiply equal -1, and then do that for a bunch of them. And how many do I have? I forget. Count. 40? So not that many actually. That's enough. Why are they not negative? The fourth one should be negative. Three, 123, 172, 3, no, 105. That's this thing. I see. I see. I'm. Ay, ay, ay. Okay. So I do need to do that and that and that. Okay. That fixes it. Now that's not a. This. Does that work on all platforms? I think it should. You might have an issue with reading it from one platform to another. There we go. Because I was casting the value here that I get from the array to a I32 rather than reading the address as an I32. So now we have a bunch of negative numbers. The negative count should be the same as here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Beautiful. Now that we have our statistics, we can start copying we can start copying the negative values first and then the positive values later. So that would be a pos count. And now we are doing I can't use that because that's a keyword, but I can use block. And there's probably a better way because I don't want to like write this every time I want to get a specific offset from the array. This is probably a good time for a macro. Maybe there's a better way to call that. Because right now, it kind of looks like I am getting the value here, but actually I'm getting the pointer at this location from this array. Yeah, we're having our block and we're having our destination. And that would be stride times positive count. And there's no offset here. If well, I need to read the value again. If the value is less than 0, then we are or maybe call it cursor. We get this destination. And this positive is plus the negative count stride times the cursor plus the negative count, because it's always above it. And right now I just realized, well, if I'm if I'm sorting it downwards up, then I want the or up to down from index 0 is the highest value. Then this is the wrong direction, I guess. I guess we'll find out. I can, again, I think maybe I should just like finish one path and then the rest of them will be more obvious. Maybe call this source then. We can call it SRC and DST. Well, I never included memcopy. Memcopy is part of string. What's it look like? Test source count. Cool. So let's just make a quick check. This is the array. Huh? Oh, did I copy the destination into the source? Silly me. Yeah, if we take a look at the buffer array, it was 40, right? We can see we have the okay. Well, that didn't work. That is good. Yeah. This is our source. Our destination. Let me open up another memory window. Source and dest. That's it's a random memory. Okay, fine. Although, why is it not aligned? this is where we are going. Times 9. So how is... Oh, we start at the wrong... I see, I see. Well, that's a problem in my allocator. Oh, I see. So the Scratch Arena right now... It looks like there's a zero terminator there. I probably want to just align that though in my allocator, arena alloc. Used plus size. Align up size. And do the same thing for realloc. And do the same thing for arena push. There we go. That is way better. Now I can do 9 and I'm in a reasonable place. So I was very scared about being unaligned there. And then we copy the memory there. Should be completely fine. 4C2F03. 4C2F03. And we go to the next value. Oh. We never increment the cursor, of course. Yeah. Ah, beautiful. So as you can see, it's populating positive and negatives. And when we get to here, we have the first 9 are negative. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the rest are positive. So that's the first pass. Now, obviously, if we are doing this up to down, the negatives should come after. So we are having a sort I32 stride count. Where did I put this? Ah, I didn't put it anywhere. We need a direction. So do I do... I don't want to copy paste the entire thing. Is that how you say it? Top down or bottom up? Yep. So if the direction is true, top to down, then the negatives are on the bottom. So the neg offset, the pos offset is equal to 0. Neg offset is equal to positive count. Else this is negative count. And this is 0. And then we just do the cursor plus offsets. There we go. So now we should be able to sort it the other way. Let's just try it quickly. Too few. So now we should be doing the same thing as before. No. No, because I gave it a true one. So the last 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 are at the bottom. If I instead do false, then they're at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now we get to the actual Radix sort. So because we are having 256 buckets, we can just kind of put that on the stack. And maybe I will do and then we can go through each one of them. It can be initialized to 0. For again, we're reading the value. We are because this is the first one, we are ending or rather now this 0xff, we should make a mask using our bucket count. This is a that good? I had some other way of making masks in my old code. Share definitions. Mask from bits. What about yoga? It also has a mask. It's the same one. So I could say 256 divided by something. It's the bucket count divided by 8. And this is a well, I mean, it kind of depends, right? Do I really? Well, I need to define a U64 one, but I don't want to use 64 for everything. But then I might as well just do this for each one. U16, U8. And then I'll just use the one that is most appropriate. Uh-huh. Minus B. What is B? Uh-huh. Uh, So I guess it's actually like this. 8 minus that. That makes sense. So like if I want to have, if I have 256 is my number of buckets, then that is 8 bits filled. So where's the 32 coming from? Because if I want 32 bits, this doesn't, here's 5 bits. I can't exactly do this. Then I get nothing. Well, it's 16 by 16, right? That's why it's 32. It doesn't make a huge amount of sense. Because I'm not using the bits. So like I can agree that, okay, this can be 32, 64, 128, 256, 512, 1024. But could it be could it be this? It doesn't make any sense. So I would assume this has to be a multiple of 2. And if it's a multiple of 2, then I can just do what I was doing before. Which is that. And it's all very simple. And then this becomes 16, 32, 64. Yeah. Then it works. So we are ending with a mask. We are having some value that we are shifting down depending on how many times we are doing this loop. Which for now I will just put it at 0, but I could imagine, you know, loop plus plus. Right. So that's our value. Now we need to count that in our buckets. So buckets value plus plus. See? See how that goes? So we're taking the value, we're masking it down to the last 256 bits, and then we are incrementing the buckets here so that we know how many there are of each. And then for each bucket, we are adding the previous. So I'm going to write this out and it's going to make sense. So TFL I32 I equals 0. Bucket count. So when we do this, we get the count of each of the values that we have, how many zeros we have, how many ones we have, how many twos we have, and so on and so forth. And then when we are doing something similar to here, we can get the sum and do the same thing with the cursor offsets. So we say that, oh, if it's a 0, we write to the bucket I plus, you know, some value, the cursor. And then if we're at 1, well, we know that the offset for 1 is the sum at that value. And same for 2, same for 3. So it's exactly the same as this thing. This offset, that's the sum. Excuse me. So then we do another for EFL I32 I equals 0, smaller than the bucket count. No, this is for the full count. Oops. And we do basically the same thing. We get the source. Which, by the way, happens to be the buffer array, I guess. So we need something like a void star write array and void star read array. And that's going to be it's funny. I was reading today about const, and that should be const, I guess. And the stride also const, and the count is also const, and the direction is also const. There's const everywhere. These are, so it's a void star const because the pointer is const, but the data is not. And then I can do this. So I'm having a slight issue. So we have our read array and our write array. And I guess we need to have a static void EFL sort swap. I know that people are talking about the ORing two things together to avoid assigning this, but I think there's literally no point. And again, here's like, yes, it's a const here. That's true. The content is different, but not because now you can see here, this is not allowed because they are const star, but I can change the content between them. That's completely fine. And then B is equal to buff. So we are doing this where we are having our negative. Then we might also say here actually that only if the negative count is something. So like we are initializing it to 0. If it's a 1, only then do we do this because we don't need to do that otherwise. But we can do the swap pointers here for write and read array. No, that's the read array. So again, we're getting the source. It's the read array. We're getting the value from the read array. I think technically we could do this at the same time as this, actually. I don't know. There's ways to maximize this. I'm not gonna think too hard about it right now. The destination. It's the right array. Times, again here, the bucket sum for the value plus the value cursor, right? Make sense? And then we do cursor plus plus. And then we do the mem copy. Yeah. See, we have buckets with 0 value. We are masking that. Still 3 because 3 is lower than 256. And then we say that the buckets at 3 is plus 1. 0, 1, 2, 3. Yes. Yes, yes, yes. And then we go for the next one, 123. Do I have any values that is over 256? Yes. $361. So if we look at 361 in hex, that is 169. 69 in hex is 105, which is what we get. Plus 1. Yep. And we do that for all of them. I do wonder about negative values. Why is it zeros? Read array. 12. That makes no sense. So first off, let's clean up a little bit. This is our read array and our buffer, 0z and DC. Yeah. Now we can look at write array and read array. And as you can see, the read is, but I'd swapped them. No? Yeah. Bad typo. What is... So that has the first pass of the sorting done. And this has the original, but we are going to write that, write it over. Yep. So now obviously we're going from the read array, which has the sorted values ish, minus 137. The value we're looking at is 119. I'm a little bit skeptical. But we'll see how it turns out. So we have our sum. It goes up slowly. 40, that is correct. There is 40 values. So I guess maybe we can assert that. We can just steal that from here. Yep. So yeah, we are asserting that. And then we get to the cursors, but I saved, so let's rebuild. Read array. Yep, that's the source. Write array is here. And we need to do it individually. Hold on. Maybe the negative would be the very last sort, and then it just kind of works. Let's move ahead like this and just see what happens, because I think all I really need to do is I take this and I'll just put it at the very end. Maybe this is a lie. So yeah, source, value, we do the same thing as before. $119. We're grabbing the destination. So the bucket at 119 is 28. Makes sense, I think. So if we open the right array, we go down to 29. Yep. We should see that here now. 29. 28. Right. Yeah, on 28. For some reason, it's not red. Not sure why. And we do that for all of them. It should be more sorted than before. I wonder, because you have 123. Doesn't make a ton of sense. Let's disable the negative values for now. So what that should do is we should not have, this should never trigger. We're skipping it completely. And then we're looking at the right array. 0, 1, 0, for some reason, 3. Yeah, I have some kind of off by 1 error somewhere. But that looks largely correct. Now you can see here, 302. Here it is. 302 in hex is 12E. So hex 2E is 46. It goes right before that. So if I would do this twice, then I would actually get the right value. But I'm having some kind of off by 1 error that gives me this right here, because this is invalid or like outside. So wait, right array. It's the right array 8. So when there's no 2. The bucket value is 9. But why is it 9? This is all 0. There's no okay, so there's 4 zeros. And there's 4 ones. No, there's 0 ones. And there's 5 threes. Bah. Yeah, that makes sense because it's the delta between here. So from 0 to 4, it's 4. 4 to 4 is 0. 4 to 9 is 5. So we are looking at right 1, 2, 3, 4. That is correct. 1, 2, 3, 4. But then something happened where there's only 4 ones, but it was reading 5 of them. So on this breakpoint, I want to break when value is equal to 3. So it's on the first one, I think, literally. 0.31, let's write it down. $32, 34, 35. So what is here? A read array. 0, yes, I got that one. 31, 3, good. 32, 3. 34, another 3. And 35, another 3. So there are 1, 2, 3, 4, 5 threes. So then the question is, why wasn't it copied? Wait, I think I know what's going on here. There are 0 zeros. Yeah. So why am I getting 4 zeros there? Never happens. Mm-hmm. I see the issue now. There we go. That was all. Oh. I'm writing zeros into everything. Oh no. What's the smart way to do this? I guess I just have to do something like one 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 3 3 3 3 3 5 6 7 8 9 10 11 15 15 15. This is probably also 15. Nice. So what if we do this to 4? Well, obviously we need to swap the pointers also at the end of the loop. I mean, that already seems to work. Yeah, the value is going to be mostly zeros because almost none of them is more than 256, or at least very few of them are. What? Okay, that's not correct. This loop needs to be times 8. Or it's based on this. It's like how many multiple of 2s it is. So you can do 256 divided by 1, 2, 3, 4, 5. Huh? Divided by 2. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I probably need to figure that out. or like bit set. And there are intrinsics for this. Which I also have somewhere. Byte swap, op count. Yeah, this bit scan reverse is the one. Although that's a Windows thing. No matching function is because this is an int to unsigned long. Which is like, okay, fine, that's true. But isn't intrin a Windows thing? Well, it's built into the compiler. Yeah. Okay. So you want unsigned long? Yeah. Expected expression. No. Bit set. Though that has to be 8. What are you complaining about? No matching function. You are confused. Yeah. Never mind. Here. So I should get back something. It's 8. Beautiful. I love it. And then I get the bit set. Otherwise, you know, whatever. Awesome. 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 Now I do need to get this from from a from a macro. So define rather if and defined MSP most significant bit, right? And we're doing this. Or result rather. Thank you, Clangd. I love that. I don't know why I couldn't do that from the start though. Funny. Anyway, now we can do Clangd, please. You're drunk. It's working. Like here, it's working. You were just upset for no reason. So now we should be able to get better results on So I think technically, when I did this loop 4 times, it did still work because I was sorting by the first bit. And the first bit was still sorted, and then the second bit was sorted, and the fourth and the third and the fourth. And then there were most of them were just sorted by then. Or maybe I was lucky. But now it should be like properly sorted. Mm. Hopla. So let's take a look here. So now it's the second loop. We have the value 1. It becomes 1. 1 becomes 1. Why is the bit set 0? I need to use the bathroom, so I'll be right back. I decided to get an apple as well. So how is it that this is not working? I have an idea why. One-handed coding. I think it just cannot. It doesn't know how to get 256 out of the definition and putting it in there. I think. No. What am I missing exactly? If defined Microsoft and not Clang, else built-in clear zero. I've written this code before myself. But do I really have to make a function for it? Or can't I just make a macro like this? And you notice, like I said, Microsoft version. So it's a Microsoft thing. It might be built into Clang, but I don't know if you can use that on Linux. Probably not. Opera. I was only a drop of water or juice, I guess. Well, if I have to write a function, I will write a function. It's just whenever it comes to these, when it comes to these things where I have to define or not define something, I just find it much nicer and cleaner to use a macro. Macros are annoying to work with in general. So I think my neighbor was screaming or something. Yeah, macros are pretty annoying to work with. Whenever you have a bug with them. Oh no. Got a piece of skin between my teeth. Yeah, whenever you have a bug with them, it's like really annoying to investigate. But okay. Let's write a function. MSC? MSC ver? Yeah. I never used GNU. GNU C. Maybe that's why it didn't work. Unterminated conditional. Where? Really? There we go. Okay, so I was just being a dummy. So then I can do the same thing here. And it's this clear 0. It's just taking the number of zeros that are, how many zeros are leading in the value. But is it, how does it know if it's a U32? Is it always U32? Int. Well, if it's int, then that's says a lot. Is it returning anything? It's 32, no? Why is it 31? One error. It's 9. So I guess it's 31 because it's starting at the first one. Oh well. 888. So we are this thing I wanted to take a look at after the swap. So again, value is 1, then it's 0, 1, 0. And they're all going to be 0 up until you get really high up. Eight, 9, 10, 11, 15, 534, 279 becomes 1. So we can see here now buckets, 36 zeros, 3 ones, 1, 2, and that's it. All the way up to 256. But of course we have to we have to actually use that result when we are sorting. We could break here, but I think it's not worth it. I value the assert here more. Checksum. So let's see some copies. How do I want to set that up? We have our read array. We also have a write array. Can put that like so. Now, most of these will be the same. So we have the first one. We'll copy this over. 40, you can see there. 52, 57, 47, 1654, 50, and so on, up until we reach here at ID 3 or 19. So 12, 13, 14, 15, 16. 17. So notice here 73, 75, and then instead of 3, we got 44. Forty-four is from where? Did I miss it? Oh, 69? Must have missed it. So 69 is this one with 27. And now we should have all the buckets in this one, as you can see. So if we would copy it over again, then nothing should change. It should be exactly the same. This one was copied here. And it's all sorted. 1, 3, 5, 6, 15. Cool. Now we can mix in the negative numbers again. In alphabet. Let's just see what we get in the right array. Would be. Okay, so we have the negative values are all at the bottom. That makes sense. But it only makes sense because we sorted it all the way until the last byte, which I don't want to do. And also you can notice that minus 250 is at the top, even though all of these, it should be the same, but they should all be here instead. Am I using these at all? No. So let's take this entire thing and just move it below. And see what we get now. Well, I think I might have forgotten to compile. Ah, I see, I see. So now they are all sorted with negative numbers. Now, this doesn't, we don't really need to do this. We can throw it in there. We have the largest value. Probably we want the smallest too. So the thing is, if there's no negative values, we don't have to keep sorting. So if there are negative values, we want to keep sorting until the end, because those go all the way up. So we can take these, throw them in here, and then we do because we're getting the value anyway here. So before we do this, if loop equals 0, yeah, makes sense. So we do this at the same time as we do the first loop. And only the first loop. We don't have to do it multiple times. Then we swap the pointers and we say if negative count right? So how do we do how do we check that? Well, we know the largest value. And if it's smaller than basically the reverse of this. Something like that. right? Makes sense. I have to double check because, you know, if this is 1 and the bit set is 8, then this is 256. And if the largest value is 255, then we can just break out of the loop and go home. And we will never encounter that in the loop that we made. So let's remove our negative values here. Oops. I think we just didn't break anywhere. Yeah, we're at loop 0. The largest value is not less than 0. So we go to the next one. The largest check is 256. Aha. But that's not true. Now, since we broke out early, we might have an issue with the arrays. So we have one final check to do. We should change this to something else. Source array. So if we don't end up with the read array as the source array, or maybe this should be a bool also. So what this copy back to source means is the function copies the data back and forth between the source array and buffer array. There's something like this you can do. I don't know how to use it. Anyway, so we're literally just doing this and this. Oh, too few arguments. True. So the source array is OC and the read array is OC. That makes sense because again, we were this largest check. We only went through this loop twice. So if you remember from the very beginning, we went one way and we went back and then it was sorted. And there was no negative values because I removed those. So if I do this, it will do it 4 times, but it will do it 1 extra time because of the negative values. And then you see 3DC and BOC. So then we do one final copy back. So this is the sorted array. This is where we're reading from, minus 250 up to 534. And you can see here, this is the same thing, except it's not sorted with the negative numbers. So we do that. And now we have in our read array the original thing. Now, if we don't care about that, because again, maybe the array data that we're getting is, maybe we have a different kind of allocator and we don't care about the extra copying back. Maybe it's a huge array or something like that. And it doesn't make sense. You use malloc anyway. Yeah. Then in here, we can do this actually. I think this is maybe better for the logic. So now we need to store that somewhere. So again, the same thing. The read array is not the same, but we are not copying back the source. We just swap the pointers. And then we get G. And G is the sorted. This is not sorted. This is not sorted at all. Okay. Let's do a void star return pointer or return array. Right? No. So if the read array is not, if the read array is the source array, then we just give back the source array. If it's not, and we don't care about copying, we give back the right array. And if we do the copy, but how does it make? Because I'm copying to the destination. Just coming up on 4 hours. Okay, now it makes sense. So if the source array is the right array, we just give it back. Otherwise, we're giving the read array. Otherwise, if we have to copy back the source, we do the copy and then we give the right array anyways. Right array anyways. There. So the return array 40. Oh. So never mind. It's the wrong. How do I keep doing the same error? But it doesn't make sense. This BOC is equal to BOC. But we swapped the pointers. Ay, ay, ay. Read. If it's the right array, we just do that. And read array. It's the right array. How do I keep getting this wrong? I don't know. Read array. We swap the pointers. We swap the pointers here too. So it should be the read array. If it's not the read array, oh, if it is the read array, we give back the read array. How does that not make sense? Aha. Okay. I was expecting it to be this one. So it is the right array, BOC. And we need to, if we need to copy back to the source, we copy from the right. Making. Why is this dumping me? I was writing the entire function with no issues. I had an apple. Copy back to source. We don't care about copying back to the source. We return the right array. And the return array, BOC, is the same as the source array. But now, I see the issue. Because we're not returning the right array. We're returning the thing that actually has the correct data. This has the right data. Otherwise, we copy it back and give the right array. Now it makes sense. So we are returning the wrong array. That's fine because that's what we asked for. And if I do something else, like for example, AB glyphs 18 if I do that, it will be no. I was thinking it would be a uneven copy count again. But because we have negative values, we go the full anyway. And then the last one for the negative values themselves. Makes sense. Oh. I haven't seen that value before. So that's like 20 U24 max. Yeah. I didn't recognize this value at all, but I guess I haven't seen it very much. The largest check is larger than the largest value. There's no negative, but we are on an uneven count. Beautiful. And then one last thing, we remove this. They are the same. We give the read array. G is good. Okay. So that's it for the stream. I have a pretty good working Radix sort, I think. I'm very happy with how that turned out. I was worried I was gonna like get stuck somewhere because I never wrote one before, but actually it was pretty straightforward, and hopefully everything everything I wrote made sense to anyone who was watching as well. But yeah, the cool thing is that this is completely independent. Like, okay, you need to have a I32 to sort, and the count needs to be also an I32. But that's why we are having possibly in the future some overloads or alternatives for that. And yeah, I might even like have a master function that is reading the sizes and everything and then calls correct one. But yeah, that's cool. So thank you very much for watching, and I'll see you next time.